We are still in our operations research course, and today we will talk about the feasible region and the optimal solution, and we will start with a focus on the graphical solution. We learned before how to build your model in order to solve a linear programming problem, and we talked about a real-life situation where you need to create a model set of equations and constraints, inputs and outputs for your problem in order to solve it in a mathematical way. So today we will talk about the basics of an important concept for solving like a second or higher level complexity problems in linear programming and operations research. What is a feasible region? Maybe this term will sound cloudy for you now, but as we're moving forward, you will be familiarized more with that concept. So feasible region is a comfort region, a region that everybody needs, optimized region you can say. So for linear programming, it's a set of all points that satisfies the linear programming constraints and size restrictions. So it's a region that defines a certain drawing, let's say, kind of linear drawing, based on the constraint we have in our model in order to represent the problem in visualized shape. So we will take some assumptions. Let's say we had a real-life problem that we analyzed and we summarized. Then we realized that that problem have a set of constraints. We have x1 larger or equal to 0, x2 equal or higher to 0 as well. We have positive numbers. Then the problem is saying x1 less or equal to 4, and it says x2 less or equal to 12, and we have 3 x1 plus 2 x2 less or equal to 18. So we have here on the right hand side x and y axis Cartesian model. Let's call this x1 axis, and this called as x2 axis. Usually in the Cartesian we're used to say that x1, I mean x and y. For the visualized solutions of linear programming, in most cases we can say x-axis is called x1, y-axis is x2, while having those constraints in mind. Okay, let's go for the simplest one. So we have x1 and x2 are positive values. So we have here positive values. So as we know here in the Cartesian method, or in the drawing in here, you can have the minus term in here and here, but since our x1 and x2 are positive value, so the x1 and x2 values will lie in the right upper side corner of the Cartesian. So that's one. So that's the branch that we want to work on, just to keep in mind. Okay, then we have x1 less or equal to 4. So that means the value of x1 can't exceed 4 for the purpose of visualization and being able to represent the x1 on the graph. We can say x1 equal 4. Just same as your basic elementary middle school math class. You just draw x1 equal 4 on the Cartesian. So that's the value of x1 on the Cartesian. I'll try to be a little precise in here. So that's x1 equals 4 on the Cartesian, right? So let's change the color here. So this is x1. Well, let's choose the black maybe for this case. So x1 equal 4. So that's the representation of that constraint. Then we have here 2x2 less or equal to 12. This can be said x2 less or equal to 6. And for the sake of graphical representation, we can say x2 equals to 6. This is where x2 equals to 6. If we take a horizontal line in this case, so we can call this x2 equals 6 line. So that's a line with an equation x2 equals 6. Then you have this formula in here. It's a little bit more complicated than the other ones. So you have a linear equation. You can say 3x1 plus 2x2 equals 18 as an equation, right? As we learned in math, just apply the basic concepts to draw that linear equation, finding your slope. If you do that, then you will find that from 9 in here, oops, let's change the color. So you have one point will intersect with the x2 or the y-axis at point 9, which is 0 and 9 to be precise, and the other point intersects with the x-axis with the point 6 and 0. If you draw a line between those two, a straight line as straight as possible. I know it's not straight, but I mean just for illustration. So you can see that you will have a region encapsulated between those lines. So between the x1 equal 4 line, oops, so between the x1 equal 4 line and the x2 equals 6 line, and this is the line for the equation 3x1 plus 2x2 equals 18. So you can see the intersected common area between all those line equations is this area right here. If I want to find another color in here, so let's go with the pink. So this is the your feasible region that you are looking for. So that should be a straight line somehow, and right here. So we don't care about this area at all, so we just care about this area. So that's your feasible region, and in the future we will take an example how to take this region after you identify it, how you're gonna take it to the next step and get the best out of it. How does this kind of graphical representation help you in finding the solution? That's what we will know next.